Hi everyone, I'm Blaze and welcome to my third video on modeling. The first one being the stochastic modeling, the second one being the ordinary differential equations, and the third, now we're entering the chemical master equation. And so I'll explain to you what the chemical master equation is and show you how it's kind of a hybrid between the two previously. But essentially what it is, it's going to model the probabilities that our mixture is in a certain state, but we'll get there. These are all the libraries I'm going to use. So stochastic simulation picks one path through the state, like we showed in that video. It picked one path and it just multiplied the probability that it would take that path of the previous state to then go on to the next state, and then multiply the probability that would enter another fork in the road and then enter that state, and over and over and over again. This is going to be different than that. But that stochastic simulation, if it's run a number of times, that model might be more telling about the state of the system, what the system is at a certain time. Now, ODEs assume a high concentration and availability of reactants and thus do not have potential change that stochastic modeling has. This is going to be closer. What I mean by potential changes is that this will be closer to the average of the stochastic simulations if you run a boatload of those stochastic simulations. Anyway, both of these have their downsides, and so you can actually have a hybrid between the two and actually create this chemical master equation. I'll refer to it as the CME from now on. The CME models the probability of a system, or that the system is in a certain state over time. This method of modeling essentially combines the ODE approach and the stochastic approach. We will use ODE integration to calculate probabilities that singular molecular models in stochastic modeling would end up settling in. So what I mean by this is that if you run a boatload again of stochastic modeling, you would end up settling in a certain proportion of roughly, or you'd see a certain state maybe show up a little bit more likely than another state. So let's consider a simple example for the CME that we'll do today. We'll just do an association and a dissociation reaction with different constants, K1 and K2, different rate constants. And so if I start with 3 x's and 2 y's and 0 xy's, we can draw this out and we would actually only have 3 available states for what our mixture would be in. So the first one would be our initial state, the count of x and the count of y being 3 and 2 respectively, while xy is 0. Then if, say, we conduct one association reaction, that will change to that. And then if we conduct another association reaction with that, with state 2, we would get 2 xy's. And so there are 3 ways, they can go back and forth between states, and we'll use that in our calculation of the probabilities of, what our mixture is going to be, or what our mixture is going to be in the state of. But that's going to be in a second. So to model with the CME, we will define our propensities by multiplying the rate constants with the reactants. So our K1 and K2 times the reactants. So also, for the sake of graphing a model that would be visually stimulating, we will set K1 equal to 5 and K2 equal to 3. So we'll have some sort of settling in on certain probabilities that weigh in, or that weigh better as we pass time. One downfall of the CME is that when species count gets high, usually this model gets tough, and the stochastic modeling ODE integration would provide better information. I would say ODE integration, if the species counts gets high, might provide you with the information you're looking for. Anyway, to calculate the probability, so this is all based on the probability that it's in a certain state, and so that's what we got to figure out now. So to calculate this probability that a state is in a current state, let's go ahead and fix that. All we need to do is calculate the probability that the system is moving into that state and subtract the probability that the system is leaving that state. That should sound familiar from the ODE video where we calculated not the probability of the system moving into the state, but the system actually moving into the state. Anyway, you can look at that if you'd like more details there. But the only thing that is now, since we are using probabilities, we must measure in a way with nothing but a basis of propensity, which is calculated by multiplying the rate constant by the count of the molecules, and thus probably in the probability that the state of the system was in that state before entering the current state, Pi. I'll represent it as P1, P2, and P3 below to coordinate with our three states defined here. So from above, if we stick on P1, I'll scroll up so we can have access to both. Change of P1 equals what we're entering, the state we're entering, times the reactants. And so if we conduct this reaction equation, we need xy to be 1. So that's the count of xy, times P2, which is the probability that we're in state 2, times the rate constant K2. And so that's going to be the probability that the previous reaction moved into state 1. Now we need to subtract the probability that the state system is leaving that state. And so that's going to be using this association reaction, and that's going to be the probability that it's in state 1, i.e. there's 3 x's, 2 y's, so 3 times 2 times P1, which is the probability it's in P1, times K1, but it ends up turning into a minus because we subtract that, which is our rate constant for that association reaction. So we can do that where it's the system moving into the state minus the system moving out of the state, the probabilities of those two, and do that for all three. You can check my work, but if we have this probability of the system moving in minus the probability of the system moving out, it should be that, and that for state 1, state 2, and state 3. And so I just kind of, I translate that into Python right here, and we will use this in our integration for ODEs. So when we define our initial state function, or the initial state of the function, we're in probabilities, right? And so probabilities, we know what the initial state's going to be. And so the probability, if I want it to be 1, if I want our initial state to be in state 1, the probability that it's in the state 1 to start with is 1. It's 100% probable that we are in state 1 to start. And so that's how the why not works in this case. These are my defined rate constants, K1 and K2. For TS, I define the time to be 0 and 2, 500 and 1 equally spaced points in between that. And then I integrate just like how we integrated with the ordinary differential equations in the previous video. Then we print out and we see the res of P0, P1, P2 similarly. And the one little gimmick that, I call it a sanity check, is that the sum of the probabilities should be 1 at all times, right? Just like how the sum of the probabilities at the initial state was 1, because it's a 100% chance that it's in state 1. It should be, the sum of all of these should still be 1 after you, or as you integrate. And so I'll just plot that to show that this probability model does work, okay? And so that's really it, okay? So we can go ahead and run that, and then if we plot, I plot the different states. So this first one is our initial state, which is our blue line here. We can see that the probability was 1 at the initial, and then it drops all the way down. Then this next one, x2, y1, xy1, we can see that drop off from 0. So both our green and yellow line dropped off from 0 because we know that wasn't the state of the initial mixture. And so these jump up and then even out, and pretty quickly, about time equals 0.5, they all kind of flat line out. And so what this represents and this is our sum of the probabilities, just to make sure this doesn't fluctuate. It shouldn't fluctuate. It should always be 1. But this is what it would look like. So you get to know, the probability that your mixture is in a certain state based on just the simple reactions like that. And so that's easy as that. It's just a little conceptually a little bit harder than, say, just the ODE or just the stochastic, because then you have to understand both of those in order to implement it here. Anyway, I hope that was helpful, and I look forward to doing some more advanced modeling now that I've set down the baseline of our 3 modeling techniques with Python.